Okay, for our next example, we're going to be using Maple again. So open up Maple if you have it. We're going to be looking at something graphically. Some things we can graph intuitively. We've graphed so many things that we're good at the graphs, but some aren't as intuitive. So for this example, let's look at the limit as x approaches 2 of 2x plus 3 over x minus 2. So again, we're going to plug directly in, and if we plug directly in, I get 2 times 2 plus 3 over 2 minus 2, which is 7 over 0. Now this one is not indeterminate. 0 over 0 is indeterminate, 7 over 0 is undefined. If I get something that's undefined, then I have to say, therefore, the limit does not exist. And this is exciting because this is our first use of the phrase does not exist. And we shorthand does not exist with DNE because we use it so often. So we know it doesn't exist, but why? Remember, when we talked about limits before, we said that if the limit from the right and the limit from the left agreed, the overall limit would be equal to that value that they agreed on. But why? We need kind of a definition why here. So let's go ahead and look at this graphically. So again, graphically we want to look at the limit as x approaches 2 of 2x plus 3 over x minus 2. So let's go ahead and pull Maple in here again. We've already used this plot, so I'm going to go back up over the top here and come up with a new one. You make sure you put your numerator in parentheses here. Now if we put in just 2x plus 3 divided by x minus 2, we're probably going to get a syntax error. And what this means is it's not sure what we want to do with 2x. We have to put an operator in there. So put in an asterisk, and then it likes it just fine. Let's right click, and again, that's the easy thing to do, is right click on something to figure out what to do and go to plots. Now this plot is just not very useful. It's not really showing us much, so we definitely need to change the scale here. Again, right click and go into those commands, or you can just click this value up here. Horizontally, it looks like on this horizontal axis what's going on that's interesting is between 0 and 5. So I'm going to go -1 maybe to 5 here just to get a little bit on the negative axis as well. So -1 to 5. And what you can do right here is instead of hitting OK, just hit apply, and you can kind of see the effect of what you just did, and you don't have to go back into the axis properties again. So next we can look at the vertical axis. And just as a try, just to see what looks good here, I'm going to go -100 to 100. And maybe that will give us a nice look at this graph. Oh, that is good. Let's go ahead and do that. So let's go ahead and hit OK. Right click copy. And we'll paste it into our journal doc, into our notes over here. And Control V, or you can right click paste as well. Shrink it up a little bit. Okay. So graphically, let's see what's going on here. Well, first of all, I note that the limit as x approaches 2 from the right of 2x plus 3 over x minus 2 is equal to infinity. This graph is going toward infinity. So this graph right here is going up toward infinity. Now next, the limit as x approaches 2 from the left is not going toward infinity. They're not in agreement. It's going toward negative infinity. So the limit from the left is equal to negative infinity. So for this particular case, the limit from the right does not equal the limit from the left. Therefore, the overall limit does not exist. So the limit as x approaches 2 from the left is equal to negative infinity. The limit as x approaches 2 from the right is equal to positive infinity. Therefore, the overall limit as x approaches 2 of this function does not exist because, again, the limit from the right does not equal the limit from the left, so the overall limit does not exist. So we can verify that numerically like we did up above, or graphically like we did here. For our next example, let's go ahead and look at another graph that should be familiar. Actually, let's run up here real quick. This graph right here actually should look a little bit familiar. This graph is a variation of the 1 over x graph. If you notice up here, and again, we can't cancel terms, we can only cancel factors. But if we looked at this, this actually ends up being a 3 over an x type of term here. So that's why it should look a little bit familiar. The graph we're going to look at next is going to be 1 over x squared. And we're going to look at the limit as x approaches 0 of 1 over x squared. Now again, we usually plug directly in. We use the numerical approach, and I get 1 over 0. 1 over 0 is undefined, and I always need to write this out. Therefore, the limit, d and e, does not exist. That's my answer. But I need to know why it doesn't exist. There could be a lot of different reasons why it doesn't exist. It might not exist because the limits from the right and the left don't agree. It could not exist because they agree at infinity. So we have to be pretty careful about that. This one is a nice little curve sketch we can do ourselves. This was on your first quiz, I believe. Just a quick curve sketch. This is 1 over x squared. So the limit as x approaches 0 from the left, the limit as x approaches 0 from the right of 1 over x squared. We want to find each of these values. So as I approach 0 from the right, this graph is going toward infinity. As I approach 0 from the left, this graph is also going toward infinity. Well, they agree. Therefore, the limit from the right equals the limit from the left. Therefore, the overall limit is infinity. However, the word limit means there's kind of a cap on this process. And because a value is infinite means it does not have a limit. So whenever I agree at infinity or negative infinity, I'd have to say, therefore, the limit does not exist. So we have had 2 DNEs for answer, does not exist, but for 2 different reasons. And so again, that's why it's important that we go through and look at these values. Let's go ahead and look at another example. With this example, I'm going to be looking at the limit as x approaches negative 3 of 2x squared minus 18 all over x plus 3. And again, our first thought is to plug directly in. If we plug directly in, I get 0 over 0. 0 over 0 is not undefined, it's indeterminate. So this is indeterminate. Whenever we get indeterminate, that means to do more work. And we'll write this so often that we're going to abbreviate this DMW, do more work. Well, what's the more work that we can use? Well, numerically, this didn't work out for us, so let's go ahead and look at this graphically. So again, let's go ahead and pull in Maple. Here we go. And let's go ahead and graph this. And so again, it's 2x squared minus 18. I'll kind of use what I already have started here. 2x squared minus 18 in the numerator and x plus 3 in the denominator. Right click and go to plots, 2D plot, and there's my graph. And this graph actually is not correct, but we'll make those changes once we get it back into Journal. So copy, throw this over to the other screen, Control B, It comes in way too big. Can shrink it down. Now, the reason this graph is incorrect is similar to why the other graph we looked at was also incorrect. Maple does not understand where points are undefined without a lot of work with it. So for this particular case, I do have a point that's undefined. If I plug -3 into the denominator, I actually get 0. So this graph is undefined, or should have a hollow point at -3. So here's -1, -2, -3. So down here at -3, that point should be undefined. So what's going on here? Well, actually what's happening is the better way to solve this particular limit is with the algebraic approach, but we don't know that yet. So I'll show you how to use that in a second, but let's go ahead and look at this graphically. First of all, we're looking at the limit from the left and the limit from the right. So the limit as we approach from the right and the limit as we approach from the left looks to be the same. Now remember, this point does not have to be defined. So the limit as x approaches -3 from the left, 2x squared minus 18 over x plus 3 is equal to -12. And I know it's -12 because back here in Maple, I can trace that function just like you would on your TI, and it gives me the y value. Okay, the limit as x approaches -3 from the right is also equal to -12. These agree. The limit from the right equals the limit from the left. Therefore, the overall limit is equal to that value that they agree on. So this is equal to 12. That's equal to my limiting value. And just because we can, we want to make sure that we can look at this algebraically as well. So this is kind of a sneak peek at the next section. Let's go ahead and look at the algebraic approach. The algebraic approach basically says, factor it and see what will happen. Perform some algebra on this and see what will happen. Well, if we factor out a 2, we're left with x squared minus 9, which of course is the difference of perfect squares, which factors into x plus 3x minus 3. The x plus 3's cancel, and I'm left with the limit as x approaches -3 of 2 times x minus 3. Now notice my limit notation is still here. Do not ever drop your limit notation. We do not want to drop the limit notation. Now we just look at this and try and analyze this numerically again by plugging in. So plugging in a -3, I get 2 times a -6, which is -12. And so we can see that these agree.